Hello, good evening. Hello. Thank you all for coming to our public lecture this evening. I'm Sarah Riley. I work in the communications team at the Royal Society of Chemistry. We're very pleased tonight to welcome Dr. Eleanor Schofield, who's going to talk to us about her work on the conservation of the Mary Rose, which is a famous Tudor wreck down at Portsmouth. So Eleanor's also one of our 175 Faces of Chemistry. So for those of you who don't know about this project, it's a project we started to celebrate our 175th anniversary, which is this year. And we wanted to showcase the huge range of people working in chemistry and doing all kinds of different things with their chemistry expertise. And Dr. Schofield is one of those faces. So before we get started, I've just got a few housekeeping points to cover. So we're not expecting a fire alarm, so if you do hear an alarm, you can leave the way you came up through the doors at the back, go down the stairs and out into the courtyard, and the assembly point is just by the statue in the courtyard. And if for any reason you can't get out this way, the screen will go up and there's another route that I'll lead you out through the Geological Society. But hopefully there won't be any fires. Also, the nearest toilets are on the ground floor, so if you just go back down the stairs and turn left at reception, there along the corridor on the left. If you've got a phone, you're welcome to tweet about the event. You can use the hashtag Time for Chem, which is a campaign we're running about giving time for chemistry. But if you're not going to be tweeting, could I ask you to turn your phones off, because we're recording the lecture and the phone signals can interfere with the recording equipment. Okay, so it's now my pleasure to introduce our chair for this evening, who's Professor Mary Ryan from Imperial College London. So Mary, over to you.
Thank you. Welcome. So it is indeed my privilege to chair this evening's session. And I realise you didn't come here to listen to me, so I will keep the introduction relatively brief. But I think it is important to understand the pathway that one goes through to get what possibly is the best job in the world, as Eleanor has done. So Eleanor is an alumni of Imperial College, where I'm now a professor. She and I started at Imperial College on the same day, 18 years ago. Not giving too much away, Eleanor. And she started on a course of material science for aerospace materials. So then she didn't realise what kind of transport system she would end up working with, but it clearly wasn't quite as envisaged. From then on, she did a PhD in my research group, which was a fledgling research group at the time, so there's lots of challenges associated with building the lab. And that was in an area of nanotechnology, making nanoporous materials for catalysis and sensors. From there, she went to Stanford, to the synchrotron light source, where she used Xray absorption techniques to look at biogenic uranium formation and uranium fixation. So this seemingly random walk of very different disciplines led her back to another postdoc position with Alan Chadwick at Kent, who I'm sure most of you, or a lot of you will know, who does a lot of work in spectroscopy. And he was at the time working with the Mary Rose and looking at how nanotechnology could be applied in archaeological settings using synchrotron radiation to map these changes. So all these different seemingly disparate paths that Eleanor had taken suddenly came together in this one space. And she eventually went to work full-time at the Mary Rose, and now she's the head of conservation and collections care. So she's essentially the head, the top person in research and collection and conservation, managing this great archaeological asset. So I've known Eleanor for 18 years, and there's just two things I would say. So one is she hasn't changed at all. When she arrived at Imperial College, she was clearly very bright, very determined, not in an overly ambitious way, but just in a wanting to learn and excited about learning new things and trying new things. And it's through this trying different things, I think, that she's arrived with such an interesting interdisciplinary approach. And on the other hand, she's changed enormously. She's grown as a scientist, and she's a brilliant researcher and a brilliant conservation scientist. As an academic, people often ask me what's the best thing about my job, and well, this is it. The best thing about my job is watching people that have come through our department and my group and end up being excellent and inspiring colleagues. So I will hand over to you.
Good evening, everyone. Thank you, Mary, for that introduction, and thank you to the Royal Society of Chemistry for inviting me to talk here today. As Mary said, I'm currently the Head of Conservation and Collections Care at the Mary Rose Trust in Portsmouth. I originally was the Conservation Manager there. I've worked there for about 4 years now, but my association went back to the University of Kent with Alan Chadwick. So my perception of working in conservation has been quite different. It went from being a scientist in a lab focused on one specific problem and a question that I needed to be answered to being in a museum and in a heritage organisation, which is a very different situation. A lot of the research we do is driven by the care that's required for the collection. So what I was going to do today was, first of all, give you an introduction to the Mary Rose, for those of you who maybe don't know everything about it. I'll then go on to give you a little bit of an insight into collection management and collection care, because as I said, this often drives why we do the research and how we prioritise it. It all comes back to trying to look after the collection. So the Mary Rose was King Henry VIII's flagship. She was commissioned in 1509, built in Portsmouth in the dockyard there using local wood from the New Forest and the surrounding areas. She set sail in 1511. She was really the first ship of the Royal Navy. She actually fought in quite a few significant battles. A common misconception is that she sank on a maiden voyage. She didn't. She sailed for 34 years. And this came to an end on the 19th of July, 1545, when she sank during the Battle of the Solent. This here is the Cowdray engraving. This was commissioned by Henry shortly after the event. It shows here, this is Southsea Castle in Southsea. This is the invading French fleet, and this is the defending British fleet. This is the Isle of Wight here, and this is where the Mary Rose went down. Henry VIII was actually there on that day. You can see him here, and he watched the ship go down. There's varying theories of why she went down. The French would like to say it was a French cannon, but we don't like to believe that. The most common and accepted theory is that the ship had undergone a lot of renovations, mostly to get more armament on it to make it a more ferocious warship. But this obviously brought the waterline up and put the ship further into the water. It was very bad weather that day. Actually, the bad weather is one of the only reasons that the French weren't successful, because this invading French fleet was actually larger than the Spanish Armada that came later. It was huge. But it was very bad weather, and the Mary Rose turned very quickly in bad weather and didn't shut the gun ports. And this resulted in a huge amount of water coming in and the ship very rapidly going down. Now, the way that they fought in those days is the ships would go alongside each other, and for that reason, they would have on anti-boarding netting to stop people getting on the ship. Now, in that situation, it stopped a lot of them getting off. So it was a huge tragedy. Over 400 people went down with the ship. Probably only around 35 survived. That's what the records tell us. There's also information that we have from the captain of the ship, George Carew. He wrote letters back to the shore before this event saying that he had an unruly crew, so whether maybe they weren't listening to what he was saying. There's also analysis that's been done now that shows that quite a lot of the crew was Spanish. It was quite common in those days. They were effectively mercenaries. They were just hired, and whether there was communication issues that they didn't hear the command for the gun ports to be shut. Anyway, the ship went down. It sank onto its starboard side. The reason that it survived and the wood wasn't attacked in the water as you would expect is it was very gradually covered in silt. There's quite a strong tide there and strong movement of water. It's only about a mile off the coast of Portsmouth, and the depth varies between 12 and 14 metres, so it's not very deep, it's not very far out. But the silt covered it gradually, and that's what preserved the starboard side that we have now. There were some initial attempts by Henry to try and retrieve some of the stuff, most importantly the valuable cannons that were on board, of which there were many. He actually hired a team of Venetians. They apparently were renowned rescuers of equipment of warships at the time. They managed to get a couple of bits, but nothing too significant. In the early 19th century, people called the Dean brothers, who pioneered diving equipment, they went down there and they took some things from the site. Now, at that point, it wasn't a protected site, so anything that you would find on the seabed was fair game, really. So they bought this off and sold it. So there are actually some bits of Mary Rose collection which are in private collections that have meandered their way around throughout the years. Every so often they do get given back to us because it's very obvious that it is Mary Rose. So then the wreck was covered, it remained there for years, and it wasn't until the 60s when a man called Alexander McKee, who was a local historian and diver, formed a volunteer group, first of all trying to find shipwrecks in the Solent, but really he wanted to find the Mary Rose. Now, obviously, what saved the Mary Rose made it very difficult to find because of a lot of the maps that they have from back then, they're quite accurate, so the location could be found, but because it was completely buried, it was hard to know exactly where. So at the time, it was quite state-of-the-art sonar techniques they used to find an anomaly under the seabed, and then with some excavation, they determined it was the Mary Rose. There was then thousands of volunteer dives over the late 60s, 70s and the 80s, hundreds of volunteers, all volunteers at this point, because it wasn't until 1979 that the Mary Rose Trust was established, and then it became a charitable foundation with employees. Before that, it was all just the drive of volunteers to try and find this unique piece of heritage. Probably a lot of you will remember this scene of the ship being raised on the cradle. This happened in October 1982. You might also remember the bit where something went and there was a big clunk. We actually have, this was one of the chains here, and it resulted in a big dent in one of the things here, and we still have that piece. But raised it was brought into Portsmouth Historic Dockyard, where it's been since then in the same dry dock, and it is actually still on this cradle. If you visit the museum, it is the same cradle, it's just not quite as yellow anymore, because it's been through a lot since then. This is the ship years ago in the dry dock. So moving back to the collection, alongside the ship, there was over 19,000 things excavated, all different materials, ranging from very small personal objects to huge gun carriages. Because this ship was getting ready for battle, it was jam-packed full of things, which obviously, for us, gives us huge insights into Tudor life, Tudor maritime life. What isn't often known is the amount of work that goes into recording all of those things. So these divers, they painstakingly recorded what it was, they gave a number to it, they looked where it was from, they recorded, say, the bay within the ship, they noted sometimes associated things nearby, the condition of it, and all of this is recorded. You then go through various steps of looking at the condition of it, determining whether you're going to stabilise it, whether you exhibit it, whether you store it, and if you put it on exhibition, how do you monitor the stability? So these are all the kinds of things that go into looking after an artefact, which essentially never ends, because then treatments can deteriorate, the artefact can deteriorate further, so we always have to keep looking after them. So in terms of the documentation, this is one of the artefact cards. This will have been filled in the 80s, I think it was. So it has who excavated it. It was an iron shot. They say where it was from and how it was raised. So that's one form of documentation we have. So every artefact has a card like this. This is a condition report. So this looks at, this is for a leather pouch. So it looks at how many pieces is it in. Does it have discoloration? What kind of precipitates are there on there? Can it be reconstructed? Does it need any kind of stabilisation treatment? And again, there's one of these for every artefact. The photography is really important, and it's very important to have the right light when you do it, because one of the indicators for us is discoloration and salts forming. And if you don't have the right light and you don't have a record, it's hard then to look back. You can convince yourself that something has changed colour and maybe it hasn't. So when everything was excavated, it was photographed, before conservation, after conservation, when it was installed in the museum, and periodically after that. And that just gives us a reference point to look back on. Also, everything is illustrated. Now, this is for artefacts where we have a concern, or it's particularly important for artefacts, where we have a concern that some of the detail might be lost over time. So these are leather book cases, basically, that have engravings on, and they can eventually start to fade. So everything that could be captured at the time was, this one's for musical instruments, there'll be engravings on it, which is, first of all, just for people to be able to understand what was there, but also for the understanding of the interpretation, it's important to record. We then get into whether we decide whether something is going to be conserved and to what level it's conserved. If you go down the route of full conservation, there's documentation, photography, illustration, there's some analysis potentially, with a wooden artifact, what's it made of, what's the level of degradation. Then you go through an appropriate stabilization, and then you need to look at the storage and the display and then monitoring. Also in that, you have to know, if you're going to invest this money into it, that there is somewhere that is going to display it. Because really then you have to ask your question, why are we going to put the money into conserving it? The other option is to passively store something. So these are documented to a degree, and then they're wrapped. Usually, say with the wood, we would put some biocide in there to stop any infestation, and they're wrapped in cling film and barrier foil, and they're stored and they're checked periodically. So we have a mixture of these at the Mary Rose, both of which cost money and require time looking after them. The treatment that then we decide depends completely on the type of material, also how much it's degraded, if there are any impurities, and as with everything else, it comes down to cost and time implications. Do we have the money there to do it? Is there a certain deadline for putting it on display? Are we going to get it done in time? So these are all the kind of things that feed into whether something is conserved and to what level it's conserved. In terms of the materials, we have a bit of everything in our collection. There's wood, leather, rope, all kinds of metals, lead, pewter, iron, brass, bronze. We also have some human remains. We have some cloth, a bit of wool, and they are all different. And each of them have different states of degradation. So it's looking at each item individually and deciding what's the best path for them. The majority of our collection is wood. A lot of the time when you look at some of the wood, initially when it's first raised, it can look pretty pristine because it was buried, and as it was buried, it was fairly low oxygen, which meant that the typical reactions you would expect wood to be damaged at, they can't function, so it stops it happening. It doesn't stop, I say it stops it happening, it doesn't stop it completely, and obviously the ship was exposed until it was buried, so there is some degradation. This is a typical cross-section of Mary Rose oak and what it would look like. You have a seemingly well-preserved interior. These are light and electron microscope images of the actual cellular structure. So in the interior, you can see it looks visually pretty good. These are the cells, and this is cellulose that goes inside the cells. And this, you can see, is all pretty well preserved. There is some water in there because this thing has got completely waterlogged from being in the sea for over 400 years. But it's okay. If you move to the outer regions where it's going to have more water flow, more attack will have happened, you can see that the cellulose starts to disappear. And this is when we have problems stabilizing it. When it's wet, of course, it still has water in there, so that keeps it stable. As soon as you try and dry that, if you didn't do anything and the water just came out, those cells would just collapse. So what we have to do is impregnate it with something to stabilize those cell walls when we start drying it. Now, the typical method for this is using something called polyethylene glycol, or PEG, as we call it. It's much easier to say that. This is a wax-like polymer, basically, that's water-soluble. And you, in the case of an artifact, or smaller objects, I could say, what we do is put it into tanks, sometimes pretty huge tanks, and we pack it full of things. And you fill it with water, and you very gradually increase the concentration of the PEG. Now, we use 2 grades of PEG too, a very small chain polymer that goes into those pretty well preserved parts of the wood, but has some water in it just to give it a bit of reinforcement. And then we have a higher grade PEG, which really seals the outside of the wood and fills those cells which were really degraded. So you have to very gradually increase the concentration because you end up with a disparity between the water and the PEG. And if you suddenly ramped up the concentration of it, then you could bust the cell walls just by doing that. So it's very, very slowly done. And the degree to which you put the PEG in is dependent on how degraded the material is. And there's various tests you can do from that to preserve it. I also should say it's a battle between putting enough PEG in to preserve it and not putting so much in that it does then look like wax. Because if you do objects and you put loads in, it looks plastic, and that completely defeats the point. all of our ethos with conservation is to do the minimal intervention to make sure that we stabilise it, basically. It's also usually supposed to be that it's reversible, but as we'll see later on, that can often be the case in theory. In practicality, it probably be very difficult to reverse some of the treatments that are done. So once these artefacts have been through this tank treatment, we then freeze dry them. Now what happens here is you go down to about -30. So you've got a water peg solution then. So the water freezes and then you apply pressure, and so that sublimates the solid straight to a gas and brings it out of the wood. Now the reason for doing this is it speeds up the drying process and it reduces how much the dimensions shrink. So it's much quicker. Something the size of the gun carriage would take a couple of months in there. And again, they're quite huge, so you can fit a lot of things in at the same time. After that, this is where the conservators' work really comes in, where they surface treat it. You will have excess peg on it, impurities, little concretions, and they painstakingly go through it all. And I think something that is not often thought about is that when you have a collection that has thousands of one thing, they end up doing a lot of the same thing, or hundreds of meters of rope. They went through and just very, very finely dissected the bits off, because obviously you're wanting to take off the bits that shouldn't be there, but you don't want to be ruining the material at all. Now, when it comes to the ship, I guess theoretically we could have built a tank around it, but it would have been huge. And also the problem would have been, being a charitable trust as we are, it's critical for us for people to be able to come and see the ship, and more importantly, to pay and come and see the ship so that we can continue looking after it and continue doing the conservation. So the only way that we could treat the ship was to spray it. So this involved having a network of nozzles around the ship. This fell down to, the ship was on the barge deck that it was originally placed on when it was raised. This is slightly tilted and filters down out of the ship hull into a huge tank, which is originally water, and again, slowly the concentration is raised up. It's a bit more complicated with that, with heating and cooling and filters and all of this stuff, and pumps, but that's essentially how it works. So one of the problems with spraying is that it takes a lot longer to get the peg in there. So the Mary Rose was raised in 82. Up until 94, it was sprayed with cold water. This was to keep it wet, stop it drying out, and to stop any bacterial activity. It was also while they were figuring out what they were going to do next and how they were going to do it and how they were going to fund it. The initial system that was put in for the lower grade peg then had to be replaced for the higher grade peg, because the higher grade peg is a solid at room temperature and needs heating. So that all had to be taken out and a new system put in. This is an ex-colleague of mine, and that's the kind of gear that you had to wear when you first went in there. This was in the early days of spraying. This photo in the middle, I appreciate that you can't really see a lot, but that's kind of the point, because this was taken one of the last days that I worked in the ship hall. This day, in fact, and it was awful in there. It was about 98% humidity, 30 degrees. You're doing pretty much manual labour in there. And this actually was just some of the safety kit that we had to have on, because obviously I had to come out for a breather. You would get covered in stuff as well, because things would come off the wood, things would come off from the barge deck, and it was just everywhere. So yeah, it was slightly unpleasant conditions to work in. Once we'd got to a point where we'd sprayed it enough with the peg, we started air drying it in environmentally controlled conditions. With something this size, obviously we can't use a freeze dryer. The only way you could do that with a larger structure is to take it apart and freeze dry it and put it back together again, which is just not an option for this. It would logistically be a nightmare. So some studies were done looking at different drying rates, looking at different conditions, and what they came up with was they scanned the ship, they looked at airflow around it with different configurations, and these air ducts here fed to air handling units outside the ship hull, which ensured that every part of the ship had the same temperature, humidity, and air velocity. If you don't have that, you end up with one part of the ship drying faster than the other, and this is when you can start to get distortion and cracking. So all of this is to try and minimise that as much as possible. If you have been to the museum, or if you go in the future, you'll notice that the gallery that you walk along is a little bit offset from the ship. This is because we have cranes there, and this is what we use to access the ship. You can walk on some bits of it, but we try not to. We obviously try and use the cranes where we can. But installing all of this, it was critical to have those there. So that's wood. Moving on to another material, iron. Again, our objects with iron range in size. It can go from small shots that are about this big up to huge anchors. The issue we have with iron, a lot of the time actually I should say, with composite artefacts, so say a dagger which would have had a wooden handle and an iron blade, you often just have the handle left because the blade is just dissolved in the seawater. Unless the iron was completely buried somewhere, then it hasn't survived. Where it has survived, over the years, a lot of chlorine has got in from the seawater, and that causes a lot of problems with corrosion. What you see here is desalination processes. So what's done is it's either left in water or in an alkaline solution, and the conductivity of the solution is measured basically. So you get to a point where you know you've taken out all the chlorine that you can, but you don't know that you've taken it all out. And this can cause problems later. The only way you can get around that, or try to minimize it, is to have it in very low humidity. And when I say low, I'm talking about 12% RH, and the running costs for that is just ridiculous. It's a huge amount of money to try and maintain those conditions. A treatment that was done back in the 80s was hydrogen reduction, where basically you heat it up and then the resultant product that comes, you get the chlorine out by forming hydrochloric acid. So obviously there's various safety implications with doing that technique. And the reason that they stopped doing it is because when you heat the iron up that far, you change the microstructure of it. So this, going back to that ethos of conservation, of not changing it, it was kind of frowned upon a bit. People's opinion of that is kind of changing a bit now, because obviously if you can't preserve it using other methods, the best way is to use something, to document it fully, and then use a method that's going to preserve it for people to be able to look at it and enjoy it. Once then you've conserved it, there's still considerations with how you're going to exhibit it. This is showing some of the pictures getting ready for our when the museum was new in 2013. It was the first time that we'd put the ship with the artefacts. We do actually have mixed showcases, and by that I mean there's organic and inorganic materials together. They're all stored at organic conditions because that's the majority of our collection, but that can sometimes have implications for the metal objects in there. But it's not just about the conditions in there, it's about how they're supported and how they all fit together. These are actually miniature mock-ups that were done by our exhibition team. They're kind of about this big. So they started at that scale, putting the whole display together. They then, each case that's in the museum, they trialled it, because as you can imagine with any building project, the window that they had to install everything kind of went like that. So they did all these trial runs, so they knew that they could just get in there, install it, and they did fantastically quickly. This is something that I can claim absolutely no credit for, but I find it fascinating how they piece it all together. You know, if you couldn't see the pictures on the right, I should have maybe done it like that. To be able to look at objects like that and then piece it all together and reconstruct it like as a boot is wonderful to me. Also, what I find wonderful is that they do it with the minimal interventions. They try and not attach anything to it, they just try and support it. So there's an example of a leather boot. There's not too many of these because it would only be the officers and the gentlemen that would have the boots. In fact, I think a lot of them were lucky if they had shoes at all. This is a barrel, and it gives you the idea of the difficulties of all of this when all the pieces there, especially when conserving these in a tank, trying to tag them all and keep the right tag with it without actually pinning it onto it is quite challenging. There may have been some tags lost sometimes. And then with the barrels, we had to actually do some work to get them back into the right position so they will form the correct barrel. This one I think is incredible. It actually on display is a full skeleton. And I think it's true that it's only actually attached in one place, and the rest of it, the perspex and plastic is just carefully positioned so that it supports the whole structure. If it doesn't go on display, we have the responsibility to store it. Once you take something into your collection, it is not straightforward to take it out again. You have a responsibility for it, it's recorded, you are audited on it basically. So there's different types of storage. There's on the bottom here, this is one of our rooms where it's been through conservation, it's waiting to go on display. These are items that are being passively stored. This is in a cellar in the dockyard. It's not very pleasant down there. These have all been passively stored and are on our next to-do list. This is a P&O container, which actually is being used at the moment to store some of our iron shot, which were originally put on display in the museum, but as I was saying before, with the conditions not being quite right for iron, they all got put on display and then rapidly started to crack and explode almost. So we had to take all of them back off display, and now they're in very low humidity in this container. And this is just some of our other stores where there's, excess materials. There's situations where we have longbows on displays, but we have over 100 longbows, so you can't put them all in the museum. So we have them in stores behind that sometimes we do tours of and things like that. Or they're available for research for people. Once the artefact is installed, we then have a series of ways that we monitor it. Temperature and RH are particularly important, as I've mentioned already. We have these monitors which read out. They are in every one of our showcases, and there's about 30 around the ship. They automatically read out to a computer system. This then generates reports weekly for us, or whatever intervals we choose. And we can look historically at the data of how it's changed. You can also set alarms on it. So if something then suddenly goes way out of tolerance, I start getting angry emails and know to react to it and start interrogating what the problem is and what we can do to rectify it. The light level is checked. This was actually checked right at the beginning when we went around the whole museum, and intermittently we'll go and check it again, just check it's not too high for the artefacts. Probably one of the most important is the conservators going around and inspecting the materials, the artefacts, and they have a checklist basically of each part of the museum, and they go around with a torch and have a good look around. It's for a variety of things. Sometimes things fall off their mount, sometimes part of the artefact falls off, sometimes there's discoloration. Either we see it or a front of house staff member or volunteer might say to us, we think something else is forming there, so we'll go take a look. Or we see salts and precipitates and things like that. So we just keep a close eye and again take photos if that'll help us if we think that gradually over time things are changing. There's also a huge amount of maintenance that goes into these systems. Our display cases each have their own control, so it has coolers, heaters, pumps, and they're all tucked away underneath, which makes it challenging space-wise, but also what's difficult for us is we're only closed 3 days a year, so any work has to be done before 10 o'clock in the morning. So if you were ever there before 10 o'clock in the morning, it's generally this mad rush of everybody trying to do all the things that they can't do when everyone's in there. And then this is one of our huge galleries opposite the ship. It's on 3 different levels, or 3 and a bit different levels really, but it's all one enclosure, and that essentially has its own plant room and control units that have to be serviced and maintained and all this kind of stuff. So, getting on to the science research. There's lots of different areas that we do science research. I'm just going to give a few examples of it. Some of the reasons why we need it. I often get asked, not asked the question, I often get a look of surprise when I say I'm a scientist working there. People naturally and understandably think of history and archaeology, and they don't know about how critical science is to conserving a collection like this. So some of the main reasons are to develop monitoring techniques. Obviously, techniques and technology change as we go along, so we can always look to advance that so we know more about the environment our artefacts are in. We want to look at existing treatments. So when I've talked about treating the wood with PEG, the decision to do that was made in the early 90s, which obviously is quite a long time ago now, and we have other people that we work with on similar shipwrecks. They're starting to see now that PEG eventually over time does break down. So we have to look at what's happening with that, and do we have to then go in and do something else? We need to understand the material properties that feeds into that, look at, how... Yeah, again, this goes back to the technology. As that advances, our understanding of the material properties change. And then developing new treatments. This can either be for our collection, or it's really kind of 2 strands. It can be for our collection, but also learning from what we've done. And so if we did it all again, what would you do differently, knowing what we know now? And then last of all, this often can be used to further interpretation. If there's an impurity found in something, if we dig around enough, we can think, oh, well, it's because it was by that artefact, so they must have been doing this. So all of that we try and then feed back into our museum. And essentially, as an overview, it's to try and preserve the collection for as long as possible for everyone to enjoy. One of the main focuses of my work has been the drying of the ship. So we were spraying right up until just before we opened the new museum. In fact, that was quite critical for being able to cut the windows into the ship, because during the construction of the ship, that was all completely blocked off. And in fact, some of you may be aware of some of the delays in opening the museum, and that was due to the challenges of trying to do conservation in a building site, basically. So the closed loop that I talked about of spraying the ship and a water tank, this water tank was designed that if any water evaporated or a little bit came off, it would automatically fill it in, which is fine until somebody comes along with a scaffolding pole and breaks the seal and you lose everything and it just chucks in loads of water and your concentration of PEG goes from 60% in water to 20%, which did actually happen just before I started working there. And then you have to very, very gradually build it up again. So that did result in some delays for us. But the main focus of my work for the first year there was preparing the ship for drying, thinking about how we were going to monitor it and how best we could monitor it with the resources we have. To that end, I got a PhD student at the University of Portsmouth and also got sponsorship from Lyco Geosystems for a total station. That's this here. This looks at prisms around the ship. They're located at these locations. Yeah, it's essentially a prism, and then the total station shines a laser and it goes to reference points on the cradle and then scans around the whole ship, and it does that 3 times a day. And what you can do then is look at the movement over time. You can also set alarms on that, so if something did suddenly drop, if it moved a certain distance, then we would be able to look at that. So what this student is doing is looking at the movement over time and seeing if there's any patterns. This was done a couple of years ago, but it shows some of the initial movement. She basically took the data from the total station and then scaled it with the arrows. So unsurprisingly to us, some of these timbers at the top are moving the most because they're kind of on their own and they haven't got much support. So that wasn't hugely surprising. It also wasn't surprising that everything is going down because it's drying and it's relaxing into the cradle. But then we start to see other patterns that, in terms of the longer parallel to the ship, that these are going this way, and then on the other level they're all going this way, and then they start to change around. So what we try and do is then look at that and look at the architecture of the ship, look at where there was breaks when it sank, and see if we can try and predict the movement moving forward. To also help us with that, we've been completing full laser scans of the ship. So this does a whole one of the entire structure. And as there's been 2 or 3 done before, we're looking at programs where you can overlap the different images. So it basically allows you to then look at a certain point and you can measure the distance over the years. So from 2016 to 2009, and hopefully, if I'm lucky, back to the kind of 80s, there was a scan then, we can kind of see over time how much the structure has moved and changed. This actually brings me to where I first got involved with the Mary Rose. Being on the seabed, you get things incorporated into wood which you wouldn't normally expect to be there. In this particular instance, we were looking at sulfur and iron, and this is the work that I started at the University of Kent. Here is a chest panel. That's a gun shield. This is a hand weapon. It would have had a metal component here. This is a hole where a bolt was into a gun carriage. And you can see with all of them, they have this nasty kind of yellow deposit, which doesn't look good, but it's also really acidic because it's sulfate and then it's forming sulfuric acid. And this can essentially destroy the cellulose in the wood, which then will destroy the structure. As I said, the sulfur and iron got into the wood under the seabed. The very low oxygen, where the traditional bacteria that would eat the wood doesn't work, other bacteria like a lot and work very well. And they interact with sulfate that you get in seawater and produce a reduced sulfur, which diffuses into the wood, basically. And this reduced sulfur, the sulfide, is kind of stable in a low oxygen position, but obviously when you excavate things, you bring it up and you expose it to oxygen, and this can lead to these problems, particularly when we start drying it. With the sulfur now, you have this kind of range of different sulfurs, from oxidized sulfur, which is sulfate and sulfuric acid, to reduced sulfur, the sulfides that first went into the wood. But you have a lot of intermediate products that can be formed along the way to the nasty sulfate that's going to cause us problems. The only way that we can look at what sulfur is there, the different types, is by using a synchrotron. This is a synchrotron this is called Diamond Light Source. It's in Oxfordshire. The way that this works for research institutions and charities like where I work is that you write a proposal, it's a peer-reviewed programme, and if successful you get time. It's usually about a 1 in 3, 1 in 4 chance of getting the time there. And then when you're there, you get slots 24 hours straight, depends what you're doing, how much time you get, typically 2 or 3 days, and you try and run as many samples as possible. Essentially how this works is the electrons are formed, they travel around in this ring here, and they are deflected, and on the point of deflection you form X-rays. These X-rays are then optimized for material characterization, and you get all kinds of research going on there. Some of the things Mary was talking about before, catalysis, nanotechnology, DNA analysis, cancer research, looking into turbines and microstructures, a bit of everything is going on there. Where the X-rays are formed and go down, we call this a beamline, and this goes into an experimental hutch. We often get asked to do quite a lot of PR for there, because obviously the Mary Rose being quite an accessible thing. So I had to do a photo shoot at the beamline, so this is me trying to stare intently at a piece of wood, which actually is quite difficult to do, I have to say. The technique that we look at is Xray absorption. This was the reason I got into doing this. As Mary said, I specialised in this when I was working out at Stanford on a completely different topic, but it's the same technique. Essentially, you're shining X-rays on your material and measuring what comes out. In more detail, what that means is you're tuning the X-ray energy for your element of choice, in this case sulfur, to below and then to above, where you will emit a core electron, and you're measuring what is emitted from that, being a photoelectron. So it's a very element-specific technique. The reason it's really, really handy for sulfur is that, as I said before, you have sulfur of lots of different oxidation states, from the sulfur that first went into the wood, the reduced sulfur, right up to the oxidized sulfur. And because each of those have a slightly different electronic structure, the resultant Zanes, the X-ray absorption technique we do, is slightly different. So the peak position is in a different place, the intensity is different, the profile is different. So in summary, it means we can take a piece of wood there and look what different sulfur is there, and look how it has been changed over time since it's been excavated. What this means for Mary Rosewood is you can look what's there. We did a bit of analysis just on a 1 centimetre cube, or slightly over a centimetre cube of wood, and we just moved the beam around and looked what sulfur was there. The first thing you notice is that this has got, as opposed to the graph before, this has got multiple peaks in. That's because there is all kinds of sulfur in there. Oh joy. So there's some original sulfur that went in, there's something in between, there's some sulfate. It's a right old mixture, which obviously makes life complicated. And to further complicate that, you move a millimetre on the sample and the proportion of one to the other completely changes. So it is very heterogeneous, let's say. In terms of the ship, when we started drying it, we obviously had to you're introducing more oxygen, and this is the very thing that is going to drive that reaction. I should also say, with the sulfur oxidation, the thing that catalyses it is the presence of ions, and we have a lot of that from all those corroded artefacts that's gone into the wood. So you particularly see the sulfur salts on artefacts that had a metal component, or things, say the chest panel that we saw, that probably was next to something, or it might have had a metal artefact inside it. It can be a bit arbitrary, really. It just depends what was near it and what happened over time. We have a programme at Diamond at the moment looking at how that sulfur evolves into the wood as we're drying it. What we do is we take a sample from the ship. So we use a corer, and you basically drill into it. You end up with a core that's around 5 millimetres diameter, and depending where you took it from in the ship, maybe 5-10 centimetres long. We then take it to the beamline, put it in, and just scan down. And this was taken when the sprays were on. You can see this murky environment. And then it's mostly reduced. There's a little bit of oxidized sulfur on the surface, which you would expect because more air has got to that part of it. Then as we turn the sprays off, we get sulfur oxidizing and going into the wood. one of the ways that we can mitigate against this is having a very stable environment in there, which we need for drying anyway. One of the first places where this sulfur process was realised was the VIII in Stockholm, which if you've never been, I would thoroughly recommend it. This is a 17th century warship which was raised in the 60s. We have a very close partnership with them. It's very good for us because they started doing everything first, so we can look at what they've done. But we exchange research and knowledge and experiences with each other. So they didn't have a climate control around the ship, it was fully conserved, and they started after a very humid summer seeing these salts forming and realised it was sulphur. So they now have a fancy system designed to kind of bring down, it's the humidity really, when it gets very humid it'll start to form it. So that's one thing we can keep control of, and at the moment just monitor it. Another synchrotron we sometimes go to is the European one. This is in Grenoble, very nice place to visit. The technique we do at Diamond, your beam of X-rays or the area that you're sampling is more on the order of 0.5 millimetre. At this particular beamline at this facility, you can take that down to tens of microns. So you can start to look at where the sulfur is in relation to the wood structure. This is some quite recent data, but it's just to give you an idea of then we can look, well, where it does a certain type of sulfur preferentially form in a certain place. And then at each of those points, we can do analysis to tell us exactly what the sulfur is. Now, all this is well and good using a synchrotron, but in a typical museum environment, you would not have somebody like me with the experience of using a synchrotron. That's quite unusual. Also, it's increasingly difficult to get time at a synchrotron facility. It can be very, very competitive. And so what we wanted to try and do was develop a cost and time effective way and a relatively user-friendly way for people to be able to look at an artefact and see whether there's sulfur there. So this is a project with Mary at Imperial College. I read a paper basically looking at sediment mats and biogeochemical processes, and they were using sulfur electrochemistry to determine whether there was sulfur there. So they would have these probes basically. So what we've been doing is first of all looking at solution sulfur data. It's ended up being a little more difficult than we thought it was. But we have been able to isolate certain reactions from the sulfur electrochemistry. We also then have been working on trying to simulate the wood samples. What's really challenging sometimes in conservation is, I've talked about having a lot of a certain artefact, but there are obviously restrictions on what I can use and what I can chop up for research, and you want to be quite sparing with how often you do that. With this particular experiment, we weren't bothered about the wood structure, we were bothered about the components of it. So we made oak powder, and we basically made a pellet with iron sulfide, and just pressed it together so we know it's got the wood and the iron and the sulfur there. And we first of all ran our iron sulfur compound in solution and got a certain profile as shown here. We then ran it with very, very small amount of solution in this pellet and managed to get the same thing. So this pellet is only about a centimetre across. The idea being that solution electrochemistry is all well and good, but the last thing you will want to do is to douse your material in liquid. You want to be able to just use a very minimal amount and get some kind of indication whether you've got a problem with the material. So that's one thing we've been looking into. The other thing we then have to think about is a lot of our artefacts, these things have already developed, so what do we do? And again, this comes down to time and cost and the practicalities of what we can do with it. This is a gun carriage that was due to go on display. These pictures are taken just after I started working there, and the conservators were concerned about it and got me down there. And you can see here, it is just covered in salts, which are a mixture of sulfides and sulfates. And not only is that damaging from a chemical perspective, but mechanically you can see there's loads of cracks on there, and it was really damaging the gun carriage. So we pulled this back from going on display. If you go to the museum, you'll notice at one point there is a cannon without a carriage. That's this one. It's not very popular that day. What we decided to do with this, there's looking at other work of colleagues around the world, they looked at ways to try and remove iron, because if you can get as much iron out as possible, then that slows down or stops any kind of sulfur oxidation. This is DTPA. I'm not even going to try and say that now. And what this does is it's a chelating agent. So this is a piece of wood, and you can see it just pulling the iron out of it, which is obviously nice when you've got a tiny piece of wood. But when you've got a huge gun carriage, this is a tank in our conservation facility. This actually, I was laughing then because the way you get things in there is the side comes off it, and getting the side back on it is quite difficult. That took quite a bit of effort. Also, what we found was difficult was this gun carriage had already gone through conservation. So when you put it back in water, it tends to float. So we had to try and tie things down and hold things down. This is one of my conservators who was getting extremely unhappy by this point. So we tied everything down. Again, trying to keep all the numbers on it too as well, so it doesn't drift off when we lose which part it is. Fill it with water first of all. This actually it's about 9,000 litres to fill this tank, so it's a huge amount of solution. Frustratingly, because of the size of the gun carriage, it's like this. So it would have been better if we could do it shallower, but we had to obviously put in a huge amount to cover that. So you put in the DTPA, a set concentration, following the kind of recipe that other people have successfully used. This is quite alkaline though, which isn't good for wood. So then you have to put in hydrochloric acid to bring the pH down, which is a bit of a strange feeling, pouring concentrated hydrochloric acid into a tank, but you're pouring such small amounts into such a huge enclosure, it just brings it down to about 3 or 4, pH of 3 or 4. This iron removal, we've taken, every so often you take samples and you basically just measure the iron content in the solution, and once you're not getting any more out, that doesn't mean it's all come out of the wood, it just means that the solution is saturated, so then you do another round. This was in 2012, we are still doing it, and we have so far taken off over 5 kilograms of iron from this gun carriage. If I'd known that before, I might not have done it, because it's taken a very, very long time. It's been ridiculously expensive. Frustratingly for me, I went through the whole process with the water company of explaining what DTPA was, which I had to order from China, I think it was, look at the levels of that in the water, look at the levels of the hydrochloric acid. I then thought I'd got through and that we'd be able to just discharge it down a normal drain. She then asked me what we were doing, and I said iron removal, and she said, well, what's the concentration of the iron? Too much, so it couldn't go down the drain. So the waste disposal is epic for this. It's probably the most expensive part of it. So for this gun carriage, it's probably it'll look at being around £15,000 to do this treatment, which is just, obviously not feasible for everything. It was the right thing to do, I think, for this gun carriage because it was breaking apart. A lot of the others aren't showing this, so we would only ever do it if it was critical to the artifact. But yeah, it's been an interesting experiment. So then we need to look at ways how we can locally treat something, because often what will happen is it's not like the gun carriage, it's not completely covered, you'll get isolated patches. Now, obviously you don't know what's going on below the surface, and again, this is one of the huge problems in conservation. You can only really treat what you can see, because it's not like you can chop it open and see what's inside. But it's kind of you do the best that you can. This, again, goes back to some of my work at the University of Kent. We looked at using strontium carbonate, the idea being that this would react with sulfates and form strontium sulfate, which is relatively insoluble in water, which means you won't end up forming sulfuric acid. It'll still be a sulfate, but it's not going to form that acid which destroys the wood. You could use other carbonates. We chose strontium, first of all, just because it's an easier marker. Other carbonates, such as calcium and magnesium, there's already that in abundance in the wood, so it makes it hard to isolate the reaction. So my work focused then on tiny bits of wood which were immersed in a solution containing strontium carbonate. We looked at Zane's again, and we looked at the wood before and after treatment. So before treatment, it had a typical sodium iron sulfate in there. After we treated it, it had strontium sulfate. So the reaction had happened that we wanted to. In addition to that, though, it had already also reacted with some of the sulfides that were in there. So we'd also got rid of some of the other sulfur that was in there. So that was kind of a bonus that we weren't expecting. Now, going back to the being in a lab and doing the experiments and then being in a museum and the practicalities of it, you can't really put a whole artifact in a solution. We can, like I did with the gun carriage, but it's going to cost a lot and take a lot of time. It's not practical. So what I first of all started looking at was making a kind of slurry really with strontium carbonate with water and just brushing it on. This was a gun carriage wheel showing these kind of sulfate salts. So I brushed on this white slurry, went away, came back, and it had gone bright orange. So basically, that obviously had iron sulfate in there, and it was forming iron carbonate that was coming out of the wood. So that was fine. So we cleaned it off, and I thought, let's just do another trial of that. We ended up doing it about 10 times, because what was happening is it was leaching the iron out of the wood, which obviously is another added bonus. So we know that we're trying to get out as much. So we carried on doing the treatment until it wasn't going orange anymore, basically. So we'd extracted as much of the iron as we could and obviously stabilised the sulphur that was there. So that kind of worked fine, but one of the problems and one of the things you don't want to do is always be introducing such a lot of liquid. So one of our conservators recently has been looking at a treatment, incorporating this treatment into a patch made of cellulose. So cellulose is good because it's already in the wood, but the great thing about cellulose is if you put a bit of water in there, it makes a putty, basically, so you can mould it around something. So we, again, simulated iron sulfur in oak. This time, though, we wanted the wood structure there. We wanted to see how this patch would react. So we soaked a load of fresh oak samples in iron sulfate solutions. We then checked that it had gone into the wood, and then we made up these patches, wrapped them around, and stuck them on. And basically, they're a bit wet, and so you can mould it around, then they dry out, and they just crack off, and they don't interfere with the surface at all. And we went back to Diamond and we did some analysis on those and realised that, first of all, in the wood, we were forming the product that we wanted to. But even better than that, some of the sulfur and iron were coming out into the patch. So it was managing to leach out some of these problem materials. So that's something we're going to be working on a bit more. Now going back to the iron. Obviously, this one here, it is very obvious that there is a problem with it. Often, though, the shot can look fine, and it's only until you look at their density that you realise that they're not, and it's basically corroding from the inside out. The opposite to that is this is a bolt taken out from a gun carriage. We took it out because it was actually weeping iron chloride, and it just was a bit dangerous before going on display. Now, this has got corrosion, but if you look inside and drill, the iron inside is like the day it was made. It's really quite incredible. So that's obviously passivated and is preserved inside. This is one of my PhD students at UCL who's now looking at the iron and looking at the corrosion and how the corrosion has varied given how it's been stored and how it's been treated. We have over 1,200 iron shot in various states, and so the ethos that we've used is that it is justifiable to sacrifice some of them and destructively test some of them to really understand what is going on. We also have a situation where we have a large subset which you can basically say are the same. They were all Mary Rose shot, they all went down, they all were underwater for the same amount of time, and all that changed is what happened to them when they came up. You often get that people try to, because it's the only way they can, compare iron, but it's from different sites and times and burials, and there's just too many variables there to really be able to conclusively say anything. This is one of the shots that UCL have at the moment. You can see here the segment that she's taken out of it, and then she's cut it into pieces. She has, again, all the information of where it was from. We always try and give that to the students, so if they find anything, they can come back and be like, right, well, what else was in that compartment? So the M refers to the main deck, and it's the 6th cabin along. This sample, we then gone to Diamond. They actually fund part of Hayley, the student at UCL, part of her PhD. And we did elemental mapping. Now, this is very recent data, but just to give you an idea of some of the work we're doing. This is the segment here in a resin. And particularly, I draw your attention to the sulfur that's in there and the calcium. And you can see bits of chlorine, and this just shows us where these are preferentially forming, and then what she's done is looked at individual places and what product has actually formed them. So this is on an untreated shot, and the next stage of her PhD will be to look, right, well, if it was treated with hydrogen reduction, what other products? If it was treated with an alkaline solution, or if it was stored in certain conditions, and we'll compare all of those to then inform our future conservation strategies. Another project, again, a student at UCL, is looking at the museum environment. This is a graph picture my student put together, and it shows you the different types of acids that can form. And you're looking at inside a cabinet, inside the museum and outside. You have, with a new building, you have materials that off-gas, you have showcases which could off-gas. We have different materials stored together, as I said before. Those materials can degrade and give off certain gases. The treatment could give off a gas, and they can all affect each other in different ways. This is a work of art we put together with different gas monitors. It was challenging because I thought we could just place them in there, but actually the bit at the bottom is the bit where the gas is analysed, so we had to tape it to this huge plastic test tube. That took some explaining to the front of house what it was. So she is going through the process of, first of all, looking what is in there, what gases are forming in there. She'll then go on to look at how much is there, is it a problem, and run tests on how that could potentially affect the artefacts. So hopefully that's given you a taster of some of the research we do there, the science research. I can't give any talk without encouraging you all to come and visit our new museum. Recently opened in July, all renovated, beautiful views of the ship and all the artefacts. Thank you all very much for coming, and I would happily take any questions.
Brilliant. Thank you, Eleanor, for a really interesting, exciting and behind-the-scenes tour. So we are open for any questions. Should be some microphones coming around. Questions, comments? Anybody? Yeah. Could you wait for the microphone? Yeah, right.
Thank you. Already 2 questions, please. If you had to excavate a large underwater wooden structure again, what would you do differently? And secondly, does critical point drying work for any of these things?
Okay, first question. I think excavation in general is looked at differently now. A lot of the kind of ethics and morals that are implemented in conservation, which actually in my opinion can go a bit too far sometimes with the practicalities of things. There are a huge amount of shipwrecks which are monitored by Historic England. They are all around the British Isles. And unless there is a place for them to go and enough interest and the money to do it, then they're left where they are and monitored, again, if there's the money to do it. The Mary Rose was quite a gung-ho example because everybody got very excited. There was royal involvement. You know, it was a huge thing. And I think probably if they found something like this again with the importance, probably they would do it again. I think in terms of the actual excavation, they were pretty ahead of the times really with how they did it and how they approached it with the conditions. They probably have better diving equipment and things like that now, which would help them. They were a bit restricted with that. I think the visibility is very poor down there, so whether they could do anything with that. But yeah, I think if somebody coughed up the money, I think they'd do it again. The second question, yeah, supercritical drying has been tested on a couple of bits, but not something that I've been involved with. I think it's just a bit more difficult to do in some ways, and having, again, going back to, it's a lot of the time, these things can work, but have you got someone there to do it for 100 of the same thing? And that can be the challenging thing.
Hello? I was just wondering, as you're well aware, the original site was under threat from various fishing activities and other things like that. And a lot of the excavation work was done under pressure of time, money, everything, as you've mentioned, and exposed very ably. At the time, there was a reluctance to look for scattered artefacts because of that, at least partly, and also things underlying the wreck site in terms of organic materials that may have migrated. At the moment, there's been significant dredging in the proximity for our new aircraft carriers, which should be arriving not too soon. Have there been many consequential finds in the dredgings from those excavations, those shiftings of the sandbanks?
Yeah, there was actually. So back in 2003, the MOD basically funded an excavation because they were going to dredge right over the top of it. And as they were funding it, we said, sure. And they found an anchor. They found the stem post, which is obviously a structurally important piece, which is being conserved at the moment. And also the anchor that I showed you, that was found then. There are other things down there, but it's not known exactly what. It's hoped that there would be parts of the bow castle down there. But now it comes down. In fact, somebody was asking me the other day, if somebody funded the excavation, would you go down and get stuff? And for me, it's not as simple as that, because we need to know that we've got the money to conserve it, that we've got somewhere to put it. So we have a lot of portside timbers, but if you see the layout of the museum here, one of the benefits for us is that it's an open ship and you have the artifacts. If I started reconstructing the ship, it would ruin the whole museum. So I would approach it with reluctance, to be honest.
I was aware of the stern post I was involved at an early stage.
Okay. No, there haven't been any others since. They're going round it. They're not near that site.
And it was relatively predictable from tide flow patterns and things.
Yeah.
And I was personally interested at the time in the possible DNA content in the mud samples underneath.
Right.
Has anything been done with that in mind at all since?
Of DNA of the mud samples, or of the...
Underneath the areas where most of the bones were found?
There's DNA analysis going on the actual human remains, but not in the sediments, as far as I'm aware.
They started to use the PEG approach. Was this a tried and tested technique, or did you have to do development work on it before you started using it in earnest?
Both. So it was used on the Vasa, so they'd already used it. There's the Bremen Cog in Bremerhaven. They also had used it. And essentially it was the best technique at the time. It still is, to be honest, pretty standard to use a two-stage PEG approach, because it's straightforward, it's easy to work out how much you need. And if I had something come in now, even though I know it can break down years, it's the best that I can do now. But this is why we kind of do the research into, for future generations, what would be their options. But they also did do trials, first of all for the PEG, looking at how the wood looked with the different treatments, different percentages of the PEG, and also looking at the drying rate, so a bit of both, basically.
Yeah, coming back to the Vasa, obviously that was in relatively salt-free water, and you have had to conserve a ship that was in salt water. Yeah. So how's the treatment differed between the Mary Rose?
So it's quite brackish water it was in, so there is still quite a lot of they have a lot of sulphur in there too. And they also had a lot of iron bolts in there, which before the problem was known with the sulphur, they replaced those iron bolts with just steel, I think. And now they're going through a process of 6,000 of them, changing them to kind of marine grade stainless steel. There are differences, but there's more similarities than differences, to be honest.
What about biological differences in terms of, say, marine life in the two environments? Because I can imagine that could also be quite different in terms of things that may have been
possibly, but I
wood.
think the resulting effect of how it degrades the wood is still very similar, as far as I'm aware. I can't say that's my expertise.
Okay, well, there is going to be time for tea and coffee afterwards, so I'm sure Eleanor will be happy to take any questions that pop into your head during tea. I'm going to thank once again, but you're not allowed to run away to ship because Sarah has got some things she wants to say to you.
Thank you. Thank you so much. That was really fascinating. I just wanted to let you know about a couple of other events that we have coming up in case they're of interest. So on the 17th of September, which is Saturday, we're going to be open for Open House Day, which is when sort of buildings around the country open their doors to let people kind of come and look at the architecture. So if you've ever been curious to kind of nosy around Burlington House in a bit more detail, that's a good opportunity to do that, and we'll have some science activities as well. And we've got some more public lectures coming up. So on the 22nd of September, we've got Dr. Victoria Hilburn from London South Bank University, who'll be talking about the contamination of water with drugs and their metabolites. And on the 6th of October, we've got the BBC's, one of the BBC science correspondents talking about sort of how he's covered science stories in the media and sort of more the sort of public, how you talk to the public about science. So if that's something you're interested in, you can look up the details on our website. And I'd just like to thank Eleanor again for coming to talk to us tonight, and that was really